So we have the 8 planets in our solar system, but what about planets outside of our solar system? Are there any? Have we found any? And if so, how do we find them? Let's go over that in this video. So very quickly to answer the question, yes, we have found planets outside of our solar system. So far to date, we found about 5,743 at the time of recording of this. That number does change as NASA discovers more and more. It's worth pointing out as well that the first planet wasn't actually found until 1991. So all of these planets that we found have been found in the last 30 years, and it's getting faster. So like the first year, there was only like 1 or 2 planets found, and then like this year, I think we found like 1,000 already. So it's getting faster and faster. Just a bit of terminology as well. So any planet outside of our solar system is called an exoplanet. You might hear me say exoplanet, I might just say planet, they're the same thing, but the scientific word is exoplanet. Similarly, you can also have exomoons. So this is just any moon outside of our solar system. As far as I know, we haven't found any exomoons. I could be wrong on that if there's any been recent studies that have found some, but they should be possible. Moons aren't that unusual, but we just haven't seen any as far as I know. So what are these 5,000 planets like? Well, the easiest way is to compare them to planets in our solar system, and this is what scientists do. So about 1,900 of them, a lot like Neptune. They're very big. They're not gassy like Jupiter or Saturn, and they probably have like hydrogen or helium in their atmosphere. And then about 1,800 of them are gas giants, so these are just like Saturn or Jupiter, very big, very gassy, there's no rocky ground or anything in there to like land on. And then about 1,700 of these are what we call super Earths. So these are they're bigger than Earth, but they're not gassy planets, they're rocky planets. And I think this is a bit of a catch-all term, because it's for ones that we know they're heavier, but maybe we don't know exactly like which ones they're most like they might have an atmosphere, they might not. And then we found 205 that are just considered rocky, so these are probably quite small, and they'd be something like Mercury. So they might have an atmosphere, they might not, but they do have a hard surface that you could land on. And then some of them we have no idea about them at the moment, but that will probably change as we learn more in the future. Why do we care about exoplanets? So the main one is look for life. So aliens, if you want to find any aliens out there and answer the big question of are we alone in the universe, then we need to try and find these aliens. So yeah, we got to try and find where they live. We want to learn more about the planets, so we think we know a lot about the planets in our solar system, but we're constantly learning more, and by looking at planets in other solar systems, we can learn a lot about our own planets too. So for instance, one thing we now know is our solar system is very unusual in that we only have one sun. Most solar systems have 2. Some even have more. So that's something that we starting to understand of, does life only exist if there's only one sun? We don't know, so it's helpful to know this stuff. And it's a very new area of science. So as I said before, it's only been about 30 years. Compare that with the study of gravity or the elements in the periodic table. Those have both been studied for hundreds of years. So 30 years is a very relatively new area of science. So it's very exciting and everyone's trying to jump in on it. So if you've seen anything about exoplanets, you might have seen their names. Their names look very weird. So here's 3 examples. So we got Kepler 581b, HD 102329c, 47 Ursae Majoris b. Now these all sound like gibberish, but there's actually a lot of information in each of these names. So let's go through them. So if we look at Kepler 581b, the first part that is a name, and it's the name of the satellite that discovered it, which is shown in the picture. And then 581 is the number of stars that have been discovered, that one is. So that's the 581st star. And then the letter is its position in its solar system. So B would be the first planet. The star is always A, and so it then shows us where it is in the solar system. Similarly, we got the next one. So HD is just the Henry Draper catalogue. This is just a catalogue of stars that someone's gone through and recorded them all. And this is the number in that catalogue. And then C means it'd be the second planet, because we got A as the star, B is the first planet, and C would be the second planet. And the last one we got is 47 Ursae Majoris. So that'd be the 47th star in Ursa Major. I don't know how well you can see, but in this little diagram, you can see the stars are numbered. And so it gives us a bit of a reference for where it is in the sky. And then B would be our first planet. An example here we've got is the TRAPPIST-1 system. So this was discovered very recently and was very popular in the news. And we've got artist impressions of what we think the planets look like. This isn't like photos or anything like that. So TRAPPIST is just like the satellite or the telescope. 1 means it was the first star found. And then we got the letters of the planets. There are some of these that break this rule, but this is good enough for now. So how do we find these planets? So there's 4 main ways we find these planets. There are many, but there's 4 that we found most of them. So we got the transit, the wobble method, microlensing, and just looking at it. So if you look over on the right, you can see that about 70% of them were found by transit, so that's probably about 4,000. 20% of them were found using the wobble method, or radial velocity is the scientific term. 2% were found using microlensing, and 1% were found using imaging, so looking straight at them. And we'll go into more detail about all of these. As I said, there are other ways, but these are the most popular. So let's start with the most obvious one of looking through a telescope at it. This is how we found every planet in our solar system, but there's a lot of problems with this. So it's only recently that we found like Neptune and Pluto, because they're just so far away, there's very little light, they're very hard to see. And this is the same when we're looking for planets outside of our solar system. They're very faint and they're very hard to see. So we've managed to take photos of a few. So we've got an example here of one. And using our decoding that we just learned. So it's called 2M1207b. So 2M is the telescope name. I can't remember what M stands for, but it's like 2 meter telescope or something like that. 1207 means it's the 1207th star discovered, and B means it's the closest one, which it looks like in this photo, but who knows, it's a very blurry photo. So yeah, we've managed to get a few pictures, but not many. The most popular method is called the transit method. So what happens is you have your star, and then the planet will pass in between the star and us, so it will block some of the light. So what happens is you have the light that's kind of, if you have it's like 100% of light, then when the planet comes, that light will dip a bit, so maybe like 90% brightness, and then when the planet moves off again, it will then go up again, so it'll be back to about 100%. And we can learn a lot of information from this. So depending on how long that blocking of light lasts for, we can figure out how fast the planet is moving. So if it's a short time, we know the planet's moving quite quickly. If it's a long time, then the planet might be moving quite slowly. And if the planet blocks more light, then we know it's bigger. And if the planet is smaller, then we know the planet is smaller. And the way scientists do this is they will watch the planets go around about 3 times before they'll start paying attention, and then they'll start looking at it more in more detail to be like, this could be a planet, because you have asteroids and comets and stuff like that moving around that do block light. So you can't just be like, oh, the light's getting dimmer, quick, let's go study that. You have to kind of watch it a few times. Similarly, we can also find multiple planets in solar systems this way. So you can have multiple planets going around, each blocking their own amounts of light. And in theory, the same could happen for moons too. But as I said at the start, as far as I know, that we haven't seen that happen. There is a problem with this transit method. Well, there's 2 problems. So the first one is you need the planet to pass between you and the star to be able to see it block the light. If instead of it going round this way, if instead the star is here and the planet goes round that way, it will never cross in between the star and us. So therefore we'll never see it transit and block the light. So you can't detect a planet that way. And remember, in space, there's no up, down, left, right. Like, these solar systems could be at any angle. So yeah, it can happen that there could be planets out there that we just can't see. This method is also biased towards big planets close to their host stars. So if you think of like Jupiter, that will block a lot more light than Pluto would. The other thing as well is if you're waiting for the planet to go around the star like 3 times, it helps if it's going very fast. You're going to see that very quickly. So like some of the early planets that we found would have they would go around their star in a couple of days. So within a week, you could see it go around like multiple times. Whereas again, using something like Pluto's orbit is about 200 years. So to see that go around 3 times would take 600 years. So we'd all be long dead by then. So it is biased towards big, fast-moving planets. So the one we got is called the wobble method. The reason why it's called the wobble method is you're looking for the stars to move slightly, look like they're wobbling. So what happens is when planets are moving around their star, they actually move the star very slightly in a circle, so it doesn't, instead of like what you think of like, everything just spinning around and the star staying still, what happens is they actually kind of pull the star off center slightly and it will move around in a circle. Now, if you're looking edge on at the solar system, what you'll see is the star going backwards and forwards. And what happens is, because this is on very large scales, we get something called the Doppler effect. So when the star is kind of moving towards us, the light will get squished and go slightly more blue. And when the star is moving away from us, the light gets stretched and it will go slightly more red. Again, the same as the transit method, you need to be edge on to the solar system to see it. If you're like, perpendicular and the planet's moving around this way, again, you won't see that wobble effect happen. But we can combine these 2 methods. So from the transit, we can work out how fast our planet is going. We can work out how big it is. With the wobble method, we can work out how heavy it is. So if we know the size and the weight of the planet, we can then work out the density of it and make a guess as to what the planet is made out of. So is it a gassy planet? Is it a rocky planet? And we can start to figure out, what kind of planets these are. Now this is a bit of a weird one. This is like proper like sci-fi, I guess. So we have this thing called gravitational lensing or microlensing. They're the same thing, but they're like 2 names for the same thing. So what happens is, say you're trying to look at something very far away and there's a galaxy or something in your way, like something very big, something very heavy. What happens is, the light of the thing you want to look at that's behind this galaxy will get bent by the galaxy. The galaxy is so big and so heavy, it can literally bend light. So what will happen is, as the light's coming, it will bend and it will come round so we can see it. The other thing that happens is you get a magnifying effect. So it's like using a magnifying glass. And so you'll then be able to see things much further away than you normally would be able to. Things look a bit distorted, but you can kind of piece it together. And you can see on the left, here's an example of what it would kind of look like. This is great because it means we can see things much further away than we normally would be able to. The bad thing is this is really random. So, space is moving, galaxies are moving around, so out of nowhere, all of a sudden, you might be able to see a planet that you couldn't see before. And if you're not prepared for that, you might not have your telescopes pointing in the right place. The other thing as well is if you say you want to take multiple measurements, like keep taking photos of whatever it is you're seeing or whatever, if the galaxy moves out of the way and that gravitational lensing effect stops, you can't see that planet anymore. It's too far away, you'll never see it again. So it's a little bit unpredictable. Okay, so we talked about the 4 main ways of finding our planets. Now that we found them, like, what else do we want to look for? So if we're looking for life, there's kind of 4 key things that we're looking for. So water, like liquid water, is an important one. Oxygen, carbon dioxide are both 2 things that we breathe, and methane, which is CH4, is also a very popular one to look for because it doesn't really exist in nature without like animals or life kind of like breathing and creating it and stuff like that. One of the biggest producers of methane on Earth is cow farts. So yeah. The thing is about this is we're looking for life that's like us, that, drinks water, breathes oxygen in, breathes carbon dioxide out, farts, when there could be a lot weirder life out there. So, you watch any sci-fi movie, read any science fiction book, and you'll see there's possibilities for very strange life out there. The problem is, if you start looking for life that isn't like us, you've got to check under every single rock out there, and that will take forever. So the idea is to try and find life like us. It might speed things up a little bit, because it kind of narrows it down. There was a scientist who kind of proposed this a few years ago, and he kind of got laughed out of science because he went a step further and said that there could also be jellyfish in the rings of Saturn. As far as I know, we haven't found any jellyfish out there, but you never know. So, talking about water first. So, when we're looking for water, we're looking for something called the Goldilocks zone. So we're looking for a place where water can be liquid so that, life can drink it. So in our solar system, like in this diagram, if you get too close to the sun, it'll be too hot. So Venus, Mercury, they struggle to have liquid water. They're way too hot. They have gas, water, and steam instead. If you get further out, like Jupiter, Neptune, Saturn, if there's any water out there, it's ice because it's too cold. What you want is where it's just right. So this is what we call the habitable zone, which is the big green bit. And you can see on this diagram that Earth is inside that, and so is also Mars. So this is why we keep looking for liquid water on Mars, because we know it's possible. We just haven't really found too much of it yet. We found little bits, but not much. And the thing to note is this habitable zone, or Goldilocks zone, whatever you want to call it, it will change depending on the star and the solar system. So if the star is bigger, it might be further out. If the star is smaller, it could be closer in. If the star is hotter, again, it could move. If the star is colder, it could move. So, it's different for every solar system. So we talked a bit before about finding different gases. So how do we actually do that? So we use a thing called spectroscopy. So what this does is, you might have seen this, if you shine a light through a prism, so like a pyramid of glass, what happens is you get a rainbow out and you get all the nice colours. What happens is gases can block different colours of the rainbow. So on the top left, we got an example of what can happen is you could have the star behind the planet, the star light kind of comes through the atmosphere of the planet and then comes to us. And then what happens is we can split it up into a prism and we get our nice rainbow. But what you'll see is there's black lines in that rainbow, like bits are missing. And that's where certain gases have absorbed the light and blocked it from carrying on over to us. So you can see in the bottom left, like things like for the red bits, there's bits of water that have blocked at the red colours. In the yellowy orange bit, we got oxygen, and in the green, we've got ozone, which is a popular gas on Earth in our atmosphere. So this is how we can kind of dig in a bit deeper and try and understand the atmospheres of different exoplanets. And this is kind of where exoplanet research is going. We've already found a lot of planets. Now we want to try and understand them a bit deeper and try and understand what's going on them. And thanks to this understanding, NASA have been able to make these very pretty posters. So they've made one about a lava planet, one about a planet they think might look like Tatooine from Star Wars, and one that has a lot of gravity. Enabled us to be able to make these really cool things. So just to finish up, if you want to dig a bit deeper into exoplanets, here's kind of a place to start. So there's 3 satellite missions kind of going on at the moment that are doing a bit of exoplanet research. So you got the James Webb Space Telescope, and this is, the big NASA telescope. As far as I know, it hasn't done too much with exoplanets recently, because everyone's fighting for time with it. But it will definitely do some exoplanet stuff in the near future. The other one we got is Gaia. So Gaia has been running for a while now, and it's doing a big star survey of mapping out a bunch of stars in our galaxy, and it's trying to find stars, and so it's accidentally finding planets in that too. And then you got TESS, which is trying to find a bunch of exoplanets. So I think its aim is to find about 5,000 exoplanets. And so far it's found about 500, just where, it's only been running for a couple of years. But it's trying to find many, many exoplanets. Anyway, I hope you enjoyed that. Thanks for watching. If you have any questions about exoplanets or about astronomy in general, feel free to let me know and I can try and answer them in the future.